Okay, this is video number 2 for uniform circular motion, causes of circular motion. The objectives of this video is that by the end you should be able to say I can describe different causes of circular motion and I can calculate the force of gravity between two objects. So first off, causes of circular motion. In the last video we learned about centripetal force and centripetal acceleration, which both point toward the center of the circle and we know is the real cause of circular motion. So really anything moving in a circular path must have some sort of force pointing towards the center, and we call that a centripetal force. But centripetal force is not just a magical force that appears out of nowhere. It's caused by everyday forces that we've already seen before in our life. So here's our first example. A girl is doing the around the world trick with her yo-yo. Okay, what is causing the circular path, or what force is responsible for that path? Well, since the yo-yo is attached to a string, that means the force that is pulling the yo-yo towards the center is tension. So in this case, the tension is always being pulled towards the center of the circle, and so tension is the centripetal force in this situation. Because centripetal force is not a force that just comes out of nowhere, it has to be a real force from something. In this case, it's from tension. Okay, so now let's look at this example. This is the Shockwave roller coaster in Dallas. If you ever go to Six Flags, it's the world's first double loop-de-loop, like back-to-back loops roller coaster. So if you are on this roller coaster, what force is going to be responsible for you actually moving in a loop? Okay, so if you think about it, the force that is pushing the roller coaster in a path is the force of the rails on the car, and it pushes it into a circle. And anytime you have a surface exerting a force, we call that a normal force. So in this case, the normal force is pushing towards the center of the loop, and that is what's causing the roller coaster to move into a circle. So you might at this point say and think in your mind, well, that doesn't make sense, because when I'm in a roller coaster, I experience a force pulling me down. If you've ever been in a roller coaster that goes into a loop, you know the sensation of feeling like you're stuck to the bottom and gravity suddenly got way heavier and you're like being glued to the seat instead of falling out, because this picture would suggest that the force is pulling you out of your seat. Well, both are actually true. The thing is that the force that you feel gluing you to the seat is actually not a force at all. It's your reaction to the normal force. And really it has to do with inertia. If there were no loop, if this track just did this and went straight up, that is what your body naturally wants to do. So the fact that you are moving in a circle against your inertia is what you really are feeling when you feel glued to your seat. And a lot of people mistakenly call it a centrifugal force, but that is not true. That is not an actual force that you're experiencing. So yes, centripetal force is the normal force pulling the car into a loop. Okay, so what about this? If you are in a car and you go around a bend, or you are driving around a curve, this curve, is part of a circle. Like you can make a whole circle like this. So it is circular motion. So what is responsible for keeping this car moving in a circle? Well, it's going to be the same force that's responsible for keeping the car moving at all, and that's going to be friction. Because as the car goes around the circle, the friction of the tires is going to be pointing towards the center of the circle and keeping it moving in a circle. Okay? Once you get rotational movement going and you're in uniform circular motion, you can generate momentum. We call it rotational momentum because you're moving in a circular path. If that rotational momentum exceeds your friction, then you do like what this car is like doing here, and you start to spin out because the friction is not enough to keep you moving in your circle, and so then you start to spin out. Okay, so what about this case? This is our last example. The moon is being held in a circular path by the Earth, and you can see the acceleration vector. Centripetal acceleration is always pointing towards the center where the Earth is. So what is causing that force that keeps the moon in orbit? Okay, well, obviously, it's gravity. Okay, so we're going to talk a little bit more in depth about gravity now. Okay, so gravity, you guys know the acceleration of gravity on Earth is 9.8, but that's actually kind of not true. It is 9.8 on the surface, but it is not 9.8 for the moon. The moon, in this last example, is not being pulled towards the Earth with an acceleration of 9.8. This right here, this A, is not 9.8. Okay? And the way that we know that is because if you actually calculate out all the orbital mechanics of this and use 9.8, you would get the wrong path for the moon. So Newton, along with his other laws, also came up with the universal law of gravitation, which states that every mass in the entire universe attracts every other mass with a force called gravity, which means you sitting at your computer right now or holding your smartphone in your hand means that you are attracting gravity of everything around you. You and the computer are actually attracting each other with a very small gravitational force. Okay, and he went further to say that so if you have these two masses, m1 and m2, Newton's third law says that if m1 pulls gravity F1, then m2 pulls with the gravity F2, and these have to be equal to each other because of Newton's third law. But he says if you separate them out by a distance called r, like a radius, then the force between them is g times m1 m2 over r squared, where Fg is obviously gravity. It's the gravity between these two objects, okay? G is what we call the gravitation constant, or universal gravitation constant, and it is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, and that's just a constant. It never changes. You're just going to have to know it or have it written down somewhere for you. Okay, r is the distance between the two objects, like you can see in this picture. It's r for radius, but I mean distance. Radius is a distance. And then you have m1 and m2, which is the mass of the first ball times the mass of the second ball in kilograms. And that will give you your force between them in gravity. So let's look at an example. Okay, Jose and Bethany are sitting next to each other in class, separated by a distance of 1.3 meters. If they both weigh around 68 kilograms, what is the force of gravitational attraction between them? So you and the person sitting next in class, you are going to have some sort of gravitational attraction between you. And, you know, that's not chemistry, but, you know, we have a lot of, you know, science words for love. But anyway, so here are our givens. The radius, or the distance between them, is 1.3 meters. And both of them have masses of 68 kilograms. And we want the force between them of gravitational attraction. So our equation is F equals G m1 m2 over r squared. Okay, it might look like a big formula, but really, I mean, it's just the same as the other ones. It's a bunch of letters in there, and they're all just numbers. So we plug in all those numbers, and we type it in a calculator, and we get 1.825 times 10 to the minus 7 newtons, which, if you take it out of scientific notation, is 0.000000185 newtons, which is incredibly small. So that's why when you're sitting in class, your chair doesn't like automatically start scooting over to somebody who's really big and heavy in your class, because even if they are really big, their mass is still going to be, or your gravity between each other is going to be very, very, very small. The only reason we are attracted so much to the Earth is because the Earth is ridiculously huge. So here's another interesting example talking about the Earth. What is the acceleration of Earth's gravity? We know it's 9.8 because we can calculate it with kinematic equations, but what if we wanted to calculate it with Newton's universal law of gravitation? Okay, well, we would have to know the mass and radius of the Earth, which is 5.972 times 10 to the 24 kilograms, and the radius of the Earth is 6.378 times 10 to the 6 meters. Okay, so our givens are the mass and the radius of the Earth, and we want the acceleration. Okay, so let's think about this. Here's the Earth, round, but anyway. So let's say you are a little man standing on the Earth, and you want to know the acceleration that the Earth's gravity is pulling you down with. Okay, so if you want to know, our equation has radius, right? So the radius of the Earth is going to be the distance between you and the center of the Earth, which is where we measure radius from, is the center of one mass to another. So if you're standing on the surface, the distance between your center of mass and the Earth's center of mass is pretty much going to be just the radius of the Earth. Okay, so when we look at our equation, okay, how could this tell us acceleration? Well, I'm going to use another equation, F equals ma, and I'm going to plug that into here. So instead of the force of gravity, that force is going to cause a mass times an acceleration, right? And this mass is just my mass. So that equals gmm over r squared. One of these m's is the Earth. The other m is me. So if this is my mass and this is my mass, then they will both cancel out. And I end up with just the acceleration equals g times the mass of the Earth divided by r squared. And so I know all those things, and when I calculate it out and plug them all in, all of these givens over here into here, I get that the acceleration of Earth at the surface is 9.792 meters per second squared, which is really, really close to 9.8. It's a little bit off, but that's because the radius and the mass are probably not very precise. So that is the end of this video, and we will talk more about Newton's universal law of gravitation and what it means actually for two objects that have mass, and the fact that everything that has mass actually attracts each other on Monday when you see me. And that's all. Good night and good luck.